Previously we have seen and actually somehow informally introduced the aspects of classical mechanics, and I also said that how Newton's law actually helps, the first two laws of Newton actually helps in understanding classical mechanics as a dynamical system. Because if you see now, these are the equations where I can have x and p as two fields, and I also have their evolution equation where this dot basically means that when I say a dot, or this is just d dt of this vector. Okay. Same thing for a scalar, if I write a phi dot, this is d dt of phi. So, this gives me the equation of the evolution, and in understanding the evolution of x, I need p, I need m, for understanding the evolution of p, I need f, which is a function of x, p and t. Now, you can see that what about this m? M actually can be written as a function, explicit function of time now. Okay. So, if I just write here m t instead of, that is redundant. So, instead of writing that, I just write here t. Okay. On the other hand, x and p, they should be here, okay, because f can be an explicit function of x, f can be an explicit function of p, explicit function of t. Okay. Whatever be the nature, according to that we have to solve, or we have to handle the situation. Now, before going to that point, I want to clarify some point which is also sometimes which causes at this level some students confusion, that is x and x dot, are they dependent or independent? So, you see that x and x dot, they are functionally independent quantities. Only when you know the form of x as a function of time, for example, then only you can do the ddt or the complete time derivative, okay, total time derivative of x, and you can get x dot. It looks that this is, I mean, this is something depending on each other. So, if I know x, I also know x dot. This is not true. For example, if I give you the value of x, so for example, position 2i plus 3j minus 5k at some t is equal to 5 seconds. Can you tell me the velocity vector at that time? So, you can say no, because you have to know the explicit form of x or the x vector in terms of t. Now, if I say x is actually 3t square I plus t j minus t cube k, then you can say okay, then you give me the t is equal to 5, 6 whatever. For that I can also tell you what will be x dot, and that is why they are functionally independent. Another point is, so that I will actually come later. Okay. So, that there is another point of initial conditions. Okay. So, till now we have just wrote two equations of evolutions for two variables x and p, and we say this is a dynamical system. Okay. Now, if I correctly remember the Newton's second law, this is p dot is equal to f. So, according to our definition, that should be m v, where v is nothing but x dot. So, I can just write v is x dot for me is equal to f, and you can write that m dv dt plus v dm dt. Okay. I can write that f. You see, many a times in nature a particle has a fixed mass in time. The mass is something which does not change, and for that most of the cases we forget this term, and we simply say m dv dt is equal to f is Newton's second law. So, this we have to understand, this is for just a specific case where your dm dt is 0. However, there can be several occasions where you can model the whole system in terms of a particle of changing mass. For example, if you just want to model the rectilinear motion of a rocket, then you just think that it is actually the best modeled as a particle with variable mass. Okay. So, you see, and also when some for example, when some raindrops they gain weight with time. Okay. So, actually you can do an extended body analysis, but you can also model very simply by a point particle which is gaining mass in time. Okay. For those systems, I will give you some I mean maybe one problem or two problems in the assignment. This dmdt is not equal to 0, and you have to be very careful in writing m dv dt is equal to f. Now, if your system has constant mass, so mt is just m constant, then for that part you can actually write m dv dt is equal to f, and this m x double dot, which is ddt of x dot, which is x double dot, will be f. Okay. Or you can say, I mean is a equivalent saying m v dot is equal to f. Okay. Then the simplified equations of classical mechanics will be x dot. So, for fixed mass m, x dot is equal to, I would say v, because now my mass is constant. Okay, I do not really need to introduce p differently. So, I just write x dot is equal to v, and v dot is equal to some f force by m, which is a constant. I can say that is another function which is f, which I call acceleration or the rate of change of velocity, and I say this is a function of x, x dot and t. This is the most general case possible. I am not saying they are the all, I mean f is always a function of x, x dot and t, but on the other hand in general they can be. Okay. Now, again another I mean very like student like confusion is that, sir, x is a function of t, you have just said x dot is a function of t, m was also a function of t, but you did not write m as a m as a separate variables, whereas for x and x dot you are writing. No, that is not the case. The point is that most of the cases when we like to express this vector, we have to check that whether we have an explicit dependence on x or explicit dependent on x dot. Okay. That means that, for example, let us say I am just saying that this f, let us say, is a function like this, some variable, some constant time x vector itself. So, here you see, here I mean the x itself explicitly appears in this. If this is the case, then you can actually, you have to write this itself and not as a function of t. Of course, the most the mathematically correct way of writing is if x t, x dot t and t. And here, for the sake of simplicity, actually whenever we said this mass is a function of t, we assume that we somehow know the explicit functional form of m in terms of t, that we assumed. If this is not the case, then also we have to write another evolution equation for mass and we can act mechanical system. We are not getting into that complexity. So, what we have done is a simple construction in the dynamical system. We are not getting into that complexity. So, what we have done is a simple construction where we actually assume that even if when m is not constant in time, but changes with time, we know exactly before even solving some situation, some external information source gave me the explicit form of m. That assumption is there. Okay. Clear. Now, I am going to start with very basic level problems, and I will then go as I promised in the introductory video, that I will mostly treat the classical mechanics and its vector formulation in this course, but I will somehow start by a very simple 1D motion and the equations associated with that. Before saying, we now have equations of classical mechanics. And this equation, which is the equation where you have the explanation of the motion, is called the equation of motion or equations of dynamics, equation of dynamics. Okay. So, this actually explains the motion. So, if you know this equation, then your initial duty is to try to solve those equations and finally to find x as a function of t and x dot as a function of t, because whenever you have a dynamical system and you try to study the motion, what is the goal? The goal is that you know the value of those field variables, let us say here x and x dot, at some given instant, and using that you want to determine their values at some posterior instant or some anterior instant, or I mean some earlier times or some times later. Okay. So, if you want to do that, you have to solve those equations. So, for solving, of course, you have to solve, if you just see it carefully, once again I am going to this equation is nothing but this equation. Okay. And so, if you try to characterize this equation is actually a second order ordinary differential equation in x with respect to time. So, here I am just trying to start with a very simple case of 1D motion. So, in the classical mechanics, as we just have seen, that the basic challenge is to solve a number of second order ordinary differential equations. You can say, well, cannot we do every time? No, it depends on the explicit form of the force F or the acceleration here in this reduced case. Okay. So, 1D motion I can simply write like, what is the equation of the dynamical equation? So, dx dt is equal to v, I just have 1D, and then dv dt is equal to I have f, which you can also write f by m, whatever you want. Okay. I am not giving the vector signs because this is only 1D. Okay. So, if I now say that how to get, so here in this case I just give you, for example, this force, that is the point where I can start solving my equations, that I have to know f, I have to know, or somehow I have to guess f, I have to model f, that is the whole challenge. If somehow in some means you can write some forms of f, and that is just I am writing for this variable, that will be easier. F is x, can be a function of x, v and t maximum. F be a explicit function of t as well, where x and v is not changing, but only t is just changing, and that changes f. If that is possible, then we can say this is an explicit variation of f with respect to t. Okay. Now, if t is changing and due to that x and v are changing and those are actually changing f, then it is an implicit dependence. I hope all of you have a little bit, you are more or less familiar to the concept of explicit and implicit dependence. Okay. I will come back to that when I will talk about the partial differentiations. Okay. So, if they are the functions of this and this is a complicated function, then sometimes you know that it is not guaranteed that maybe it can be solved, but maybe you do not know how to solve that. Okay. So, that is why we have to go case by case and not to claim that this actually guarantees. If I know this, I know what is x t and x dot t, that I do not know. But in general what I can do, I can case by case I can make some strategy so that I can solve the system. The first one is the easiest one. So, my force or the acceleration, I mean just here acceleration is just a function of t only. It is just changing with time explicitly, but not with x and v explicitly. Okay. If this is the case, then you actually have dv dt is equal to f t, and if you can solve that, so that will basically give you v is equal to integration f t dt plus some constant of integration c 1, and that you know dx dt, v is dx dt because of the first equation, you just put that, and that is now this integration f t dt plus c 1. Okay. Now, you integrate once again and you have x is equal to integration of integration f. Since this is already integrated, I can use a dummy variable for this t, and this whole thing is now again integrated over time t plus c 1 t plus c 2, which is another constant of integration. Okay. In this way you can find x, and also I mean once you have the whole form of x, you can write dx dt, you can calculate dx dt, and you can have your v. Okay. So, you see in this way you can also solve the problems of classical mechanics in more than one dimension. Now, let us say you have a force which is a function of x, for example, then what to do? Then we will actually write another form which is much more helpful, is this. Instead of writing that, we can write dv dt as dv dx dx dt. Okay. Since this is just a problem in one dimension, I can write always this thing. This thing is not exactly possible, this type of writing in more than one dimension. In more than one dimension, we have to do something which we call partial differentiations. Okay. We will do like that. That is also another problem I will discuss in the next lecture maybe. Okay. So, if you write that in f x and then you see this is your v. So, you then have v dv is equal to f x dx, because v dv. So, this is v. So, this will be actually v dv dx, and that will be f x, and you have dv square over 2 is equal to f x dx, and if you integrate it will give you v square by 2 is equal to integration of f x dx. Okay. Of course, plus some c 1 constant. Then you can write this as v is equal to root over, I mean plus minus, that is also another point, 2 integration f x dx plus c 1, and then what you have here in this part, what you have something, you see you have something which is already, that was a function of x, which is already like now integrated over x. Okay. Now, you have something which can be at most a function, a constant or a function of t. Okay. That is the possibility. Now, let me just think, since our initial assumption is f is just a function of x, then t also will not come here. So, here you are actually saved. So, if you somehow know this thing, then actually your, I mean if it is integrated, then this will be another just a function of f actually. Okay. Just a function, sorry, just a function of x here, yeah, because this is indefinite integral, this will be a function of x. Let us say it is a function of, let us say g x. Okay. So, then what you have to do, this v will now be plus minus root 2 g of x plus c 1. Now, you have another function of x only, Now you can write this v as dx dt and take that one in this side with dx. So, finally, your thing will be actually dx over root 2 g x plus c 1 is equal to dt, and then you integrate both sides and 2 g x plus c 1 is equal to dt, and then either you use the proper integration like that, or if you have some formula known, you can use that. You can finally have actually some function I would say, I am just getting mathematically correct, some function h of x, which is some function some t plus c prime, another constant of integration which comes here. Okay. And then you can invert, if the inversion is possible, you can invert, and finally, you can get x as a function of t. Okay. All these possibilities are here, and you see that even if you follow a specific possibility, it is not guaranteed that always you can come out with a solution as an elegant solution like x and xt. All these conditions are also to be satisfied. Okay. And if, for example, again the last one, if f is a function of v, then what happens? I am just telling you the general strategy, then the specific problems we will do later. If f is a function of v only, then what to do? Then I can simply say that dv dt is equal to fv. This case is also very easy. You just take this dv by f of v and dt, then you integrate both sides, and finally, first you get v as a function of t, and actually what you get is not exactly that, you get t as a function of v. If that function is invertible, then you get first this, and then once you get this, you can write dx dt as a function of t, and you can integrate to get x as a function of t. Okay. So, our objective is to find equations of motion to, I just change the color a little bit, to x t and x dot t. Okay. And if, for example, f is a function of neither v or x singly, but both f, x and v, or let us say x and t, or v and t, or all these three things, then you have to check case by case, where you can solve this problem by something called separation of variables, by simplifying, by doing some other methods, by reducing this to some easy variables or something. So, there is no general prescription for that. Even in 1D, you see that the classical mechanics, which sometimes sounds very mundane, very ordinary to us, very non-interesting to us, actually is extremely complicated. Simplicity just arises because we try to make them simple most of the time. Okay. So, if we just want to do some small problems, and after that we will wrap up this lecture. So, the first one is this one. So, f is equal to e to the minus t. I have to solve, and I have to find x t and x dot t. So, that is the goal of classical mechanics. So, then dv dt is equal to e to the minus t. If I integrate once, I should get minus e to the minus t plus some c 1. Then I can write this is dx dt, right. So, I should write like here. So, this is dx dt actually. So, then x should be, I can save one line by writing this, x will be again e to the minus t, because another minus will come here, plus c 1 t plus C 2. This is the general solution of this equation. Now, you see there is a very interesting point, that is, if I just say that I give you the value of x, then what will be x dot? You can say okay, x dot is minus e to the minus t plus C 1, that is exactly what I got here. But can I, given a value of this, may I say something on x dot at that point? Let us say if I say at t is equal to 3, I give you the value of x. If I do not provide you the value of t and the value of x at that t, if I simply say that from this one, can you tell me what are the values of x and x dot at t is equal to 3? The answer is no. So, just knowing the general solution cannot help us to know the motion of the particle. You need to know the initial condition. Since this is a second order ordinary differential equation, this one, finally what you are solving is v dot, which is second order in x, d2x dt2 is equal to something. So, actually you need two initial conditions, or equivalently if you think that this is a combination of two first order ordinary differential equation, then also you need 1 plus 1 two initial conditions, okay, to completely specify that. And then you can actually see that if I tell you now at t is equal to 0, x is equal to 0 and v is equal to minus 1, then immediately you can say at t is equal to 0, this is 1 and this is 0. So, x is also given 0. So, that is why C 2 will be minus 1, right. And if C 2 is minus 1, then you can actually from this one also you can say something about C 1 easily. At t is equal to 0, this one is 1. So, this is minus 1 and v is minus 1. So, C 1 will be 0. Then the solution, the particular solution for this system is, specific solution for this system is x is equal to e to the minus t minus 1. Now, if you give me any t, I can give you x and v as well, because v is nothing but minus e to the power minus t. Okay. So, you see you get rid of the arbitrary constants of integration by using the initial conditions. So, classical mechanics is all about knowing the position and velocity for constant mass system, position and velocity of a particle at a given time. Okay. It is all about to predict or to know accurately the position and the velocity of the same particle at a later time, both by using that information of position and velocity at the some given time and the solving the equations of motion. So, there are two parts. You have to know the system of equations, you have to solve them, and also you have to know in addition the information of position and velocity at any single time instant. If you give me that, I can trace out the whole trajectory for you. Now, before wrapping up this lecture, I would like to comment on something. If you just check something, what we discussed already in the first lecture, that you have here two equations, this already, and I say that this somehow completes here. If for simplicity I can just think that if can be at best a function of x p t, or for constant mass, this is just a minute, let me go to the thing, yeah, for constant mass this is just x dot is equal to v and v dot is equal to some f, which is a function of x dot and t. So, it somehow gives us that we have a closed system at this x dot level, x double dot level. Okay. So, because if you go to x dot, you have velocity, but if you go to x dot to x double dot, you have the reason of that motion. Now, whenever you have the reason or the explanation for the motion, your dynamical system is closed. Okay. Because here actually what you are doing when you are saying that x double dot is equal to f, but that f is actually something external. If you read carefully Newton's law, this is an external agent. So, that f should be external. So, Newton's law basically says something very courageous, something very bold. It says that the second law or the first law, whatever, I mean you can combine both, actually both this first and second law actually says that you can relate, and that is the beauty or marvel of the classical mechanics, you can think, which is totally some intrinsic motion property of a particle, you can relate that exactly to something, and actually in some units that is exactly equal to something external which you call force. Now, since this is external, you know that. So, you have this information, okay. And if you know that, that is why you are just using this information to know the x double dot, and you backtrace and you obtain x. So, this is the approach of classical mechanics. Okay. So, that is why Newton's law is so beautiful and so great, because it helps in simple cases to close a system in just the motion in just up to second order derivative. Now, this is not the end of the story. In nature you can actually find several systems and several instances where you need more than second order derivative, higher than second order derivative, for example, third order derivative. So, third order derivative, many of you may know, it is called third order derivative opposition is called a jerk. Okay. I invite all of you to have some reading on that on internet, under which circumstances that can actually be important to understand the mechanics of a particle. Thank you very much.